All right, so this is the first example for impulse. So we have this figure is an overhead view of the path taken by a race car driver as his car collides with the racetrack wall. Just before the collision, he is traveling at a speed v initial of 70 meters per second along a straight line at 30 degrees from the wall. Just after the collision, he is traveling at a speed v final of 50 meters per second along a straight line at 10 degrees from the wall. His mass M is 80 kilograms. So A, we want to know what the impulse on the driver is due to the collision, and B, the collision lasts for 14 milliseconds. What is the magnitude of the average force on the driver during the collision? Now we know two things, two equations for impulse. We know that impulse is force times time, and we also know that impulse is a change in momentum. Now here we're not given force. We have to find that for part B. So because we're not given force, we can't use force times time in order to find impulse for part A. But we are given a mass and we're given an initial velocity and a final velocity. So because of that information, we know that we can find impulse from the change in momentum. Now, since initial velocity and final velocity are both at angles, we have to split these up into x and y components and find the x component of j and the y component of j impulse before we find the net impulse. So in order to do that, I'm going to draw a little picture first. So here's our wall. We know that this is our initial velocity of 70 meters per second, and then this is our final velocity of 50 meters per second. Here's our 10-degree angle, and here's our 30-degree angle. So this right here will be our initial velocity in the y direction. This right here will be our initial velocity in the x direction. This will be our final velocity in the x direction and our final velocity in the y direction. All right, so let's find what these are. So initial velocity in the x direction is going to be 70 times the cosine of 30. And then final velocity in the x direction, initial velocity in the y direction is going to be 70 times the sine of 30. And then our final velocity in the x direction will be 50 times the cosine of 10. And then final velocity in the y direction will be 50 times the sine of 10. So we'll do all that in our calculator. So 70 times cosine of 30 is 60.62 meters per second. And then of course, sine of 30 is 0.5. So this is 35 meters per second. And then 50 times cosine of 10 is 49.24. Whoops. And then 50 times the sine of 10 is 8.68. All right, so now let's find the initial momentum and the final momentum so we can then find the change in momentum. So initial momentum in the x direction will be equal to mass times initial velocity in the x direction. And then instead of doing this we'll just do this all together. It just makes it easier. So change in momentum in the x direction will be mass times final velocity in the x direction minus initial velocity in the x direction. So mass is 80 kilograms. Final velocity in the x direction is a positive 49.24 minus initial velocity in the x direction is a positive 60.62 meters per second. So here we end up getting 80 times 49.24 minus 60.62, and we get a negative 910.4 kilograms times meters per second for a change in momentum in the x direction. And then our change in momentum in the y direction will be equal to mass times final velocity in the y direction minus initial velocity in the y direction. So mass is 80 kilograms times final velocity in the y direction, and this is going to be a negative number. Now, the reason for this, if you look at our picture right here, this final velocity in the y direction, I'm going to call down negative and up positive. So that means initial velocity in the y direction will be positive, final velocity in the y direction will be negative. So we get a negative 8.68 meters per second minus the initial velocity in the y direction, which is positive 35 meters per second. So here we get 80 times the quantity, negative 8.68 minus 35. Oops, I put 25. And we end up getting a negative 3,493.6 kilograms times meters per second. So we're not done yet. We now have the change in momentum in both the x direction and the y direction. Now we have to find the magnitude of the impulse, and we'll find the angle as well. So they didn't ask for unit vector notation or magnitude angle notation. So because they didn't ask, we can just find the magnitude angle. Of course, if they ask for unit vector notation, you can just stop there. Your 910.4 will be your I hat, and then your 3,493.6 will be your J hat. So our magnitude of the impulse will be the square root of 910.4 squared plus 3,493.6 squared. I don't put the negative because a negative times a negative is a positive. And this ends up being 3,610.27. Now let's talk for a second about the units for J. Now we know again, impulse J is equal to change in momentum. It's also equal to force times time. So you can either use kilograms times meters per second. You can also use newtons times seconds for force times time. Those units end up working out. So if I use newtons times seconds, remember a newton is a unit for force, and force is equal to mass times acceleration. So because of that, a newton is a kilogram times unit for acceleration, which is meters per second squared. And then if I multiply this by seconds, you can see that that seconds and the squared cancels out, and therefore we get kilograms times meters per second. So whether you use the kilograms times meters per second or newtons times seconds for the unit for your impulse J, they both work out, okay? So you can use either one for that. So here is our magnitude of our impulse there. And then in order to find the angle, we know that the x component of the change in momentum or the impulse is equal to a negative 910.4. So that is our x component there. 910.4, and then our y component is a negative 3,493.6. That is not drawn to scale. And so this right here is our angle. Our angle then is going to be the inverse tangent. Ooh, I wanted to write a J for some reason. So angle will be inverse tangent of 3,493.6 over 910.4. Which ends up being 75.4 degrees. Now, usually they want this angle from the positive x-axis. So if they want the angle from the positive x-axis, remember this is positive x, and then this was the angle that I found here. So in order to find this angle, which is really the one that I would want, usually, I just subtract what I just got from 180, and then I end up getting 104.6. So this angle right here is equal to 180 minus 75.4, which is equal to 104.6 degrees. And of course, that's a negative because it's going beneath that x-axis. So if we want to get really technical, then the angle of impulse here will be a negative 104.6 degrees. Now, that's for all for part A, so we're not quite done yet, but part B is pretty easy. So it says that the collision lasts for 14 milliseconds, and we want to know the magnitude of the average force. Now, of course, for part B, we know that impulse is equal to a change in momentum. We also know that impulse is equal to force times time. So we just found what impulse is. We know that our time is 14 milliseconds, so we can find our force now. So force is equal to impulse divided by time. Our impulse that we found was 3,610.27 newtons times seconds. So 3,610.27. And then, of course, milliseconds, we have to convert that to seconds. So 14 divided by 1,000 ends up being 0.014. And we end up getting that our force is equal to really big, 257,876.4 newtons. All right, so we have a very, very big force causing this change in momentum. And of course, the direction of this force is going to be in the same direction as the impulse that we found in part A.